the previous video, you were introduced to the principles of sketching, as well as some simple features such as extrusions and revolutions that could be used to create parts. In this video, you will be introduced to the pattern tool, as well as a new feature called a sweep, and a new document called an assembly. Let's begin by going over the pattern tool. I'll start by creating a new part. Let's sketch a circle on the front plane, centered at the origin, and give it a dimension. Now let's extrude this to give it some depth. Now let's go ahead and create another sketch on the front face of the part. And let's create a circle. Let's give the circle a dimension. Let's set a distance between the center of the circle and the origin. You'll note that the circle is not yet fully defined. Let's set a relation between the center of the circle and the origin. Accepting this sketch, let's create a new feature of an extruded cut going through the part. Suppose we wanted to make multiple cuts. How would we go about doing that? One powerful tool is called the pattern tool. Let's first look normal to the surface. Note the pattern button here. By default, there is a linear pattern. Using the drop-down, you'll find a number of other kinds of patterns. Linear patterns, circular patterns, mirrors, and various others. Let's go ahead and click a circular pattern for demonstration. It'll first ask you, in this gray highlighted box, what is the feature to pattern? Using the fly-down menu, I'll select the extruded cut as our feature to pattern. Next, you need to define the axis for patterning. I'll select the central axis here. Recall that if you don't see this axis, you can go to your Hide and Show items on your view controls and tell it to view temporary axes. I'll select this axis and then set some parameters here for our circular pattern. So, for example, I could create a 360-degree span, allow for equal spacing between all of the patterns to be featured, and then set the number. And click OK. This creates the desired number of features that are patterned around this axis. You can not only pattern your features, you can also pattern 2D sketch entities. I'll go ahead and delete this, and I'll go back to the sketch that was used to create the original extruded cut by right-clicking and going to Edit Sketch. I'll view normal to the surface, and instead of using a linear sketch pattern, I will use a circular sketch pattern. Note that we are using the sketch pattern tool within a sketch, meaning that we are patterning a 2D entity on the plane in the sketch. So in this case, you don't select a pattern axis, you select a point about which to create your pattern in 2D space. I'll select the origin, and for the entities to pattern, I'll select this circle. In a similar fashion as you saw for the feature patterns, you can then set the number and the spacing between the number of sketch patterns. You can click OK, and note that 2 new circles have been created using this tool. By accepting this sketch, the change will be propagated to your feature, in this case an extruded cut. And we wind up with the same part that you saw when we were creating a circular pattern of the features. Later in this video, we will introduce assemblies that feature many parts fitting together in three-dimensional space. We'll find that there's another tool that's used for patterning parts within an assembly file. Next, let us introduce a new feature called a sweep. For this, I'll create a new part, and as before, create a new sketch on the front plane of a circle centered at the origin and giving it some dimension. We now have a sketch of a circle existing on the front plane in 3D space. The sweep feature allows us to take this cross-section and extrude it along a line. This line does not necessarily have to be a straight line. It could be any kind of curved path that the user chooses to define. Let's go ahead and create another sketch that defines the path for which this cross-section will be swept across. We'll need to create a second sketch. In this case, I'll create a sketch on the right plane. Let's look normal to it. Let's start with a simple sketch, a line with one point at the origin, and we'll give it a horizontal relation made by SolidWorks Inference. Let's give this a dimension. And accept. Let's take a look now at what we see. It's a circle that exists on the front plane and a straight line that exists on the right plane, whose endpoint lies at the origin and whose other endpoint is at a certain fixed distance away. We now have everything we need to create a so-called sweep feature. You can now find this under Features. In this case, we'll create a swept boss/base. SolidWorks now asks for two sketches to be inputted into the sweep. The first being the profile of the sweep, which you can think of as its cross-section. We'll use this circle as the cross-section or profile. I won't select it in the graphics area. As a good practice, I like to use the flyout and select the appropriate sketch. In this case, sketch 1. Next, SolidWorks asks you for the path along which this profile will be swept. The path in this case will be this straight line. That straight line was made in sketch 2. And that's it. I can click OK. We've created a part that involves a sweep, where this circle is swept along a path defined by a second sketch. That second sketch in this case being a straight line. You'll note that this is equivalent to an extrusion. In fact, extrusions are simple special cases of sweeps. Sweeps that have a straight path that gets for the profile to be swept across are extrusions, and they're common enough that extrusions are provided as their own feature. Sweeps are more general and allow you to take the profile and sweep it through any sketch path that you define on one or more sketches. Let's go back and edit the sketch that was used to create the path, in this case, sketch 2. Rather than use a straight line, let's use multiple lines and create a path that meanders about on the YZ plane. I'll go ahead first and change this dimension and start to add some new lines. I'll go ahead and add some dimensions to these lines now. to define a new path along which we can sweep the original cross-section or profile to create a new part. I'm using arbitrary dimensions at this point. This path is yet relatively simple, as I've only used straight lines. You could of course use any kind of a path using the spline tool or the arc tool to create more complex paths. After accepting these new dimensions, I'll accept the new change in the sketch, and let's see what the sweep now does with the propagated changes. Sketch 1, which defined the profile to be swept, has not changed. Sketch 2, which defines the path along which the profile is swept, was changed to this meandering path that exists on the YZ plane. You'll note that SOLIDWORKS has automatically created the tangencies that are necessary for these parts to fit together along the sweep. If you define your path incorrectly, SOLIDWORKS might not be able to solve the sweep path. Let's take an example. Suppose this length was shortened to 10 millimeters, as was this one. If we accept this change, we'll get an error that says that the sweep could not be completed because it intersected itself while passing through that segment. Let's go back and edit the sketch and try and understand why. The dimension of this circle is 100 millimeters in diameter. If one were to try to take that and negotiate this curve, you'll note that there's self-intersecting geometry here. In other words, the curvature of the path for the sweep should not be very much smaller than the dimension of the profile that needs to be swept. I'll increase these back to about 100 millimeters. Which should allow for the sweep path to be resolved. As an analogy to this, we can also do a swept cut. Let me create a new sketch on this face of another circle. I'll make the center coincident with the origin and dimension this. For example, how about 80 millimeters in diameter? And click OK. We now have a third sketch. I'm going to use this third sketch as the profile of a swept cut. By clicking on Swept Cut, I'll first click a sketch that defines the profile. I'll use the flyout again and select Sketch 3. As before, SOLIDWORKS asks us for a path along which to sweep this profile to cut out material. I'm going to extend out Sweep 1's feature and reuse the same path that was used for the swept boss/base. This will now sweep out along the same path a cut of a circle of slightly smaller diameter. If I click OK, we now have a hollow tube. You may see this better in the wireframe. Sweeps are very powerful when you have a constant cross-section that has a complicated profile. An important note is that for a sweep, you must define the path on one sketch and the profile on another sketch. You cannot have both the profile and the path on one sketch. They must be separate sketches in order for the sweep feature to be utilized. Now let's introduce you to the concept of an assembly file. let's create a new SOLIDWORKS document. Instead of creating a part, we're going to create an assembly file, which is a 3D arrangement of parts and/or other assemblies. When you click OK, SOLIDWORKS will ask you to begin your assembly. It says, select a component to insert, then place it in the graphics area. There are no open documents, so I'm going to have to browse to find a part file to begin our assembly. I've created a few parts here. Let's select plate 1. When I've selected plate 1, you'll see this part. I can go ahead and place this anywhere. Now we're ready to begin assembling with other parts. You'll note that we now have a new tab here called the Assembly tab. You'll be able to insert other components, which are parts or other assemblies, by clicking here and repeating the procedure. For example, I'll add now plate 2. And I'll add another component. How about a shaft? And a sphere. I've now added 4 parts. These exist in 3-dimensional space. We now need to begin to assemble these to form some kind of a contraption. SOLIDWORKS uses something called a mate in order to define the relationships in 3-dimensional space between the various parts. Before we go about doing that, let me turn your attention to the left-hand side. You'll note that we have 4 parts listed here. Plate 1, which was put into the graphics area first, plate 2, shaft, and sphere. If you expand any of these out, you'll have access to all of the various features and geometry aspects, in other words, the planes that existed within their own reference system for that part, for all 4 of the parts that are placed in our graphics area now. If you make changes to any of your parts while you're in the assembly, these changes may or may not propagate back to the original part depending on your settings. So I urge caution, and generally for novice users, I recommend that you do not change any of the features of your parts within an assembly. If you wish to change features such as length or depth of extrusion of any of the parts, you should go back to the part file, upon which when returning to the assembly file will update to reflect the changes that you made to the original part. Also, please pay attention to the notation next to each of these parts. There's an F in parentheses next to plate 1, while there are minus signs in parentheses next to plate 2, shaft, and sphere. The F means fixed in space. By default, the first part that you place into the graphics area in an assembly will be fixed in space, which means you cannot move it. All other parts will move relative to that part. The minus sign means that the part is free to move around. To show this, you can use Move Component, or if you use the drop-down, you can also Rotate Component. If I try to use Move Component, you can click and drag any of the parts in 3-dimensional space. Use caution, perspective may be deceiving. For example, if I were to change our view orientation to a 4 view and try to move around parts in the 3-dimensional space, you get a bit more control than if you were simply trying to move it around from your isometric view, which moves your part in all 3 axes, X, Y, and Z, simultaneously. If you're manually moving around parts, I highly suggest using these views so that you're only moving in one axis. I'm going to return back now to a single view and demonstrate that if you attempt to move plate 1, which is this one, you'll get the following message: the selected component is fixed. It cannot be moved. You can only move the other parts in our assembly. If this is not your intent, you can right-click on the part that is fixed and select Float. Float means that the part is free to move in three-dimensional space. Float is denoted by this minus sign, which is the same as that which appears between or before all of the other parts. Now, all four parts are able to move freely in three-dimensional space. Sometimes it's good practice to fix one part so that you have a basis upon which to build your assembly. However, this is not always necessary. Let's begin to assemble this by introducing the concept of a mate. You can add mates by clicking on the Mate button, which has an icon of a paperclip. You can read the text which says, positions two components relative to one another. If I click on Mate, you must select two entities to mate. Note when it says entities, that does not mean the part. That means an entity on a part. So for example, we could create a mate between the cylindrical surface on this shaft and, if I were to zoom in, the cylindrical surface of this hole. Note that SOLIDWORKS has attempted to move one or both of these parts so that they satisfy a kind of mate. SOLIDWORKS will also typically default to a value of concentric when you're selecting two cylindrical faces. I'm okay with this, so let's click OK. We now note that if we were to attempt to move these two components relative to one another, that no matter what, this mate holds these two surfaces concentric to one another. If we wish to fully define everything in three-dimensional space, we'll need additional mates. Let's first attempt to fix these two components relative to one another in space. We have a mate that sets the cylindrical surfaces concentric to one another. We still yet have to position the shaft relative to the hole. One possible way to do this would be to select the flat surface on the cylindrical shaft and the front surface of plate 2. By default, SOLIDWORKS has attempted to do a coincident mate. In other words, it has tried to make these two surfaces lie on the same plane. If that's not what your intent was, you could, for example, set a distance between the two. I could, for example, define the distance as 500 millimeters. That distance being the straight distance between the two faces. Suppose I didn't want 500 millimeters. I can change that to 1000 millimeters. If the direction there is wrong, you can flip dimension. I'm going to go with a coincident mate and click OK. If I attempt to move any of these components, you'll note now that the two parts move together. That's because now there are two mates that need to be simultaneously satisfied: the concentric mate and the coincident mate. There is still a degree of freedom. These two parts can rotate relative to one another. Perhaps it might be easier to see if I were to fix the shaft in place. I'll right-click Shaft and scroll down to Fix. There's now an F next to shaft, meaning it can no longer move at all in three-dimensional space. Now let's see what happens when I try to rotate plate 2. You'll note that there is still another degree of freedom. If that's your intent, then you can leave it as is. But perhaps I do not wish to have any degrees of freedom. How might I go about fixing the rotation? Well, there's two ways to go about doing this. Under mates, for the concentric mate, if we right-click that, we might have an option to lock the rotation. This locks the relative positions of the two parts in the current configuration that's shown in the graphics area. Another way to do this might be to create a mate not against one of these features that are easy to click in the graphics area, but perhaps one of the geometrical planes that exist within the reference coordinate system of this part. Let me show you what I mean. If I were to extend out shaft 1, I can show you what is the front plane of the shaft, the top plane of the shaft, and the right plane of the shaft. When creating mates, you can also utilize these. So for example, what would happen if I were to select the right plane of the shaft and try to create a mate with the right plane of plate 2? In this case, SOLIDWORKS has tried to make them parallel. If this is the correct orientation, you can go ahead and select OK. Or you can define an angle between those two, for example, 45 degrees, 60 degrees, anything you might imagine. And you could utilize these to be able to set the relative angle between the two parts. Now when I try to rotate, say the plate, I can't. You get the text that says the selected component is fully defined. It cannot be moved. If that is your intent, you now have 3 mates to define the 3 degrees of freedom between these two parts. There's 2 other parts here. Let's go about creating some new mates that set the relative positions of these parts relative to the 2 here that exist in space. For example, let's create a new mate between this surface and this surface. That may look strange to you, but I assure you, if you rotate around in 3-dimensional space, you can see what SOLIDWORKS has done. In this case, the 2 planes, or the 2 faces that you've selected on these parts, are going to be coincident with one another. Of course, one can also flip the mate alignment, which means that the 2 parts will still have these 2 planes coincident to one another, but one of them will be flipped around. Watch carefully when I hit anti-aligned. Again, this face and this face remain coincident, while this has flipped its orientation in space. Let's go ahead and click OK. Create a new mate. Let's create another concentric mate between the cylindrical surface here and the cylindrical surface of plate 1. And click OK. Now if we want to set the relative rotational degree of freedom, which we can verify exists by attempting to rotate this component, we can do so either by repeating the procedure shown before, which creates mates between the reference planes that exist in the reference coordinate system local to each part, or we can create a mate, for example, that exists between this face and this face. In this case, we're creating a parallel mate it says that these two faces exist on planes that will be parallel to one another, which now fixes its position in space. You'll note that when a part is fully defined, it no longer has a minus sign next to it. So now there are three indications here that you should pay close attention to in your assemblies. F, which means fixed in space, minus, which means float in space, which also is synonymous with underdefined, or no symbol at all, which means that that part is fully defined by the mates. At any given time, you can extend out your mates and edit these by right-clicking and saying Edit Feature. You can delete or modify as you see fit. We have one more part here. We can go ahead and move it about if we care to. Let's create another mate to position the sphere. If you select the surface of the sphere and the surface shown here, by default, we're going to create a tangent mate. When working with spheres, tangent mates are one of the easiest mates to use. It may not look tangent, which means let's rotate our view. Now we can see that there is a plane that is tangent to the sphere that is lying in the same plane as this face on plate 2. If I accept this tangent mate, I can move this component around, but it'll always be tangent to that plane. As you can see though, the tangency is on the wrong side of the plane. In an assembly, SOLIDWORKS does not really know that there's three-dimensional geometry. And so, one three-dimensional geometry can very easily clip through and coexist within the same solid volume as another part. Pay close attention to your mates to avoid these problems. I'll go back to this tangent mate, edit the feature, and flip our mate alignment. In this case, we'll maintain a tangency mate with the tangency being on this side of the face chosen on plate 2. Now when we attempt to move this part around, we can do so and maintain the tangency that we expect. But note that it's very easy for the sphere to move exactly through the shaft. Let's create another tangent mate, this time between the cylindrical surface and the spherical surface. Click OK. Now when we attempt to move the ball around, it can do so while maintaining both tangency to the cylindrical surface and to the flat surface. If one wished to fully define the position of the sphere, a third mate would be necessary. One possible way to do so would be to select a face that exists, say this face, and mate that to one of the reference planes that exists for the sphere. Let's select, for example, the right plane. In this case, it attempts to make the right plane that exists within the local coordinate system for the sphere and to make it parallel with this face. If we click OK on that, we note that the sphere is still underdefined. We can move the ball around, but we've restricted how it rolls. The ball can no longer freely roll around because it has to maintain the relationship of parallelness between the right plane and this plane. To fully fix the position of the sphere in space, we need another mate. For example, we can select this plane, or rather that face, and one of the planes on the sphere. For example, the front plane. We could set a distance of, say, 210 millimeters away. There would only be one point that satisfies this distance mate, along with all of the other tangency mates that we've already set for the sphere. Now the sphere is fully defined in space, the plate is fully defined, and the shaft is fixed. We now have a fully defined assembly. You'll note the analogies between assembly mates and sketch relations. In sketch relations, you are setting relations between entities on a two-dimensional sketch that set their relative geometries and orientations. In a similar fashion, in the assembly, you're using mates that set the relative geometries and orientations between different parts in three-dimensional space. One key in an assembly is often to try and be able to select the face with which you need to create a mate. This means that you need to be able to rotate the part freely in three-dimensional space. You can do this by holding down your middle mouse button and rotating. You can use the direction keys on your keypad, up, down, left, and right, to change your view of the graphics area. Often, you will find that it's not enough to simply rotate your view in order to see the features that you wish to create mates between. If you go to the assemblies tutorial and the assembly mates tutorial, you'll have an opportunity to gain practice with a tool in SOLIDWORKS called Select Other. The Select Other tool appears while trying to create a mate when your cursor is in the graphics area and you right-click once. You'll have the option to Select Other. If we try to select Other, you'll see that there's a few options for different faces that appear. In brief, what Select Other does is SOLIDWORKS creates a line between the perspective of the user and the position of the mouse cursor and extends that line through all of the solid model. Any features that it intersects will show up in the Select Other box. So if a feature is occluded or hidden behind other parts in your assembly, simply placing your cursor approximately where you think the assembly feature is that needs to be mated, right-clicking and seeing if you found it on Select Other gives you a powerful means by which to select features, including faces and occasionally edges and vertices, that could be used for your mates that you otherwise can't easily see from any perspective. Lastly, in this video, let's revisit the concept of patterns as it applies to assemblies. On the Assembly tab, you'll find a linear component pattern, or, using the drop-down, other kinds of component patterns, including circular patterns and others. Let's see what a linear component pattern can do for us. There are a number of things that we need to define to create a linear pattern in an assembly. We need to define the directions for our linear patterns, as well as the components to pattern. Let's begin by selecting our components. In this case, I will select everything in the graphical area. All four parts will now be the components that we pattern. For our directions, it's often convenient to utilize feature entities that exist in your graphical area that coincide with the feature directions. For example, suppose I were to select this edge. An arrow appears which defines the direction that we will pattern along. You'll need to define the spacing of your patterns. For example, let's try first 500 millimeters, and the number of patterns. For one instance, we have the original. For two, we can create a second, or a third, or a fourth, and so on. Simultaneously with a linear pattern, we can pattern in the opposite direction. For example, let's select this edge. We can increase this distance. Again, 500 millimeters sounds reasonable. And increase the number of instances from 1 to 2 to 3 to 4. If I click OK, we now have patterned all the entities that originally existed in the sketch and created a 4x4 array, reproducing all of the original features. This shows up as local pattern 1, which contains many of the copies of all of the parts. There's an important caveat to being able to create a pattern. To illustrate this, I'm going to go into my mates, and I'm going to delete the mate that exists that fixes the position of the top plate relative to the bottom plate, which will allow the top plate to have an additional degree of freedom, allowing it to rotate. If I were to try and rotate that top plate, you'll note that the top plate rotates on every single instance that exists in the pattern. In other words, using this pattern, we are creating copies of the original instance, and any changes to that original instance get propagated to the copies in the pattern. If you wanted to have truly independent instances that don't change when you make changes to the original instance, you need to utilize a tool called dissolving. If you right-click on your local pattern, the first option under the text box will say Dissolve Pattern. When you dissolve the pattern feature disappears, and all of the patterned parts are now listed as independent parts. If I were now to attempt to rotate the component on the original copy, it will only rotate on the original copy. Similarly, I can rotate this component on every other instance. But more so than that, if I were to attempt to move a component, I can freely do so. In other words, when I dissolved my pattern, I created a whole new set of parts, none of which we've mated. So patterns are a double-edged sword. You can create identical copies that copy not only the mates between the parts, but also the relative orientations, such that when you make any changes to a mate or an orientation, they propagate to all of the instanced copies. Or you can decide to dissolve your pattern, in which case you'll have a large number of additional parts with no mates to coincide with them. So I urge you caution when you dissolve your patterns, but you'll probably need to be able to dissolve patterns depending on whether or not you wish to perform an analysis of your assembly, where each of these constituent instances or copies of your parts need to act independently. I encourage you to frequently save your assembly files and to save as a copy, so that when you decide to dissolve a component pattern and find later on that perhaps it's not easy to undo that decision, you can go back to your saved copy and reperform the analysis work from that point forward.